Imagine standing above an oil field. Beneath your feet is a vast reservoir containing billions of barrels of fluid and rock. But there is one fundamental problem. You cannot actually see it. You can drill wells. You can collect seismic data. You can analyze cause, pressure, production, and fluid behavior. You can build sophisticated geological models and run millions of reservoir simulations. And yet, the underground will always remain partially unknown. This is the central idea behind Deciding the Underground, a book by Andi Anriansyah about geology, reservoir engineering, risk intelligence, and most importantly, decision-making under uncertainty. The book begins with a powerful misconception. Many people assume that if we build better models, collect more data, and use more advanced technology, we will automatically make better decisions. But the book argues that this is not necessarily true. A model can become more sophisticated while the decision becomes worse. A geological interpretation can become more detailed while its fundamental assumptions remain wrong. A reservoir simulation can be perfectly calibrated to historical production and still fail to predict the future. And an economic model can become increasingly precise while hiding the risks that matter most. So, what is the real problem? The problem is not simply a lack of technical knowledge. The problem is how different kinds of knowledge are connected. Geology creates a picture of the reservoir. Reservoir engineering tries to understand how that reservoir behaves dynamically. Economics translates technical outcomes into financial consequences. Risk analysis evaluates what could go right, what could go wrong, and how uncertain those outcomes really are. And management ultimately has to make a decision. The danger occurs when these disciplines operate as separate stages instead of as one integrated decision system. That is why the author introduces the Subsurface Decision Intelligence Framework, or SDIF. The purpose of this framework is not to eliminate uncertainty. That would be impossible. Instead, its purpose is to help organizations make better decisions while uncertainty still exists. And this distinction is extremely important. The objective is not to know everything about the reservoir. The objective is to know what we know, recognize what we do not know, understand how that uncertainty affects the decision, and act accordingly. One of the most important ideas in the book is that the geological concept is the primary decision variable. Before engineers create a reservoir simulation, someone has already made assumptions about the geology. Is the reservoir continuous? Is it compartmentalized? How are the sands connected? Where are the barriers? How do the faults behave? Where are the high permeability pathways? These assumptions influence almost everything that comes afterward. Well placement, production forecasts, water breakthrough, pressure behavior, recovery factor, and ultimately, project economics. If the underlying geological concept is wrong, making the engineering model more sophisticated may actually make the problem worse. You may simply become very precise at modeling the wrong reservoir. This leads to another important lesson. History matching does not prove that a model is correct. A model can be adjusted until its historical production matches reality. But matching the past does not guarantee that the model represents the real geological system. Instead, unexpected behavior should be treated as information. Suppose the simulation predicts pressure communication between two wells, but the actual field shows very little communication. The easy response is to adjust a parameter. But the better question is, why is the reservoir behaving differently from our model? Perhaps the fault is sealing. Perhaps the reservoir is compartmentalized. Perhaps the geological architecture was misunderstood. The mismatch is not merely a technical problem. It is evidence. It is the reservoir teaching us something. This way of thinking is central to the book. The underground should not be treated as a problem that we solve once. It should be treated as a system that we continuously learn about. And that brings us to uncertainty. The book makes an important distinction between the reservoir itself and our model of the reservoir. The physical reservoir exists, but our knowledge of it is incomplete. Therefore, uncertainty is not simply a property of the rock. It is also a property of our model. A model may appear highly confident because it has been carefully calibrated. But confidence in the model should never be confused with certainty about the reservoir. This is one of the reasons probabilistic thinking is so important. Instead of asking, "What will production be?" we should ask, "What range of production outcomes is possible, and how likely is each outcome?" Instead of focusing only on one expected NPV, decision-makers should examine the entire distribution of possible economic outcomes. Because the average can be misleading. Imagine two projects. Both have an expected value of $100 million. At first glance, they look identical. But Project A has relatively limited downside. Project B has a small probability of catastrophic loss. Their expected values may be the same, but their risk profiles are completely different. This is why the book argues that the distribution matters more than the expected value. Decision-makers need to understand not only what could happen on average, but also what happens in the downside. What is the probability that the project fails? What happens if production is significantly below forecast? What happens if the reservoir is compartmentalized? What happens if water arrives earlier than expected? And perhaps most importantly, can the organization still change direction if the original strategy proves wrong? This introduces another major concept in the book. The value of information. Not all information is equally valuable. A company can spend millions collecting additional seismic, drilling appraisal wells, conducting pressure tests, or installing monitoring systems. But the important question is not simply, would this information be interesting to have? The better question is, what decision would this information change? If new information would not change the decision, its technical value may be real, but its decision value may be limited. This is the essence of value of information. And the concept becomes even more powerful when combined with flexibility. Sometimes the best strategy is not to commit everything immediately. Instead, develop in stages. Invest a smaller amount. Observe the reservoir. Learn from production. Then make the next decision using better information. In other words, uncertainty can sometimes be managed not by eliminating it, but by preserving the ability to adapt. This becomes especially important when we consider why oilfield projects fail. The book discusses drilling failures, production forecast failures, and development strategy failures. A dry well, for example, should not simply be recorded as a failure. It should become a source of learning. Was the structure wrong? Was the reservoir absent? Was the reservoir quality overestimated? Was the charge assumption incorrect? Each type of failure tells us something different. The same principle applies to production underperformance. When a field produces less than expected, organizations often try to adjust the model. But sometimes the problem is deeper. The original development concept may simply be wrong. And this is where organizational behavior becomes important. Companies often continue with a strategy because they have already invested significant money in it. Changing direction can feel like admitting failure. The book describes this as escalation of commitment. One solution is to establish decision triggers before development begins. For example, management might define specific pressure, water cut, gas-oil ratio, or production performance thresholds. If those thresholds are crossed, the development strategy must be reviewed. This makes adaptation part of the system. It does not depend on whether an individual manager has the courage to challenge an existing plan. The book then turns toward technology. Today, oil fields generate enormous amounts of data. Real-time monitoring, permanent sensors, machine learning, digital oil fields, and artificial intelligence are transforming the industry. But the book takes a deliberately cautious position. More data do not automatically mean more knowledge. And artificial intelligence does not eliminate geological uncertainty. AI can recognize patterns. It can process enormous datasets. It can accelerate simulation. It can identify anomalies. It can help generate forecasts. But it can also fail when it encounters situations outside its training data. This is particularly dangerous in subsurface decision-making because many important decisions involve extrapolation. The future reservoir may not behave like the reservoirs represented in historical datasets. Therefore, AI needs geological grounding. The book's message is not that we should reject artificial intelligence. Quite the opposite. AI can become extremely powerful. But it should be treated as an amplifier of human capability, not as an unquestionable authority. The same principle applies to digital twins and autonomous reservoir management. In the future, we may have systems that continuously combine geological models, dynamic reservoir simulations, real-time field data, and optimization algorithms. These systems may eventually recommend, or even execute, some operational decisions. But the book argues that the boundary between human and machine authority must be carefully designed. A simple and reversible decision may be appropriate for autonomous AI. A high-consequence and irreversible decision should remain under human accountability. The more powerful the technology becomes, the more important governance becomes. And this brings us to the final part of the book. After examining geology, engineering, uncertainty, data, technology, failures, and organizational design, the author identifies 7 enduring principles of subsurface decision intelligence. First, the geological concept is the primary decision variable. If the fundamental geological concept is wrong, technical optimization cannot fully rescue the decision. Second, uncertainty is a property of the model, not the reservoir. The reservoir exists independently of our confidence in our model. Third, integration is an epistemic commitment, not simply a workflow step. Real integration means geology and engineering continuously challenge and improve each other. Fourth, the value of information is defined by decision relevance, not technical interest. Information matters when it can improve a decision. Fifth, the distribution matters more than the expected value. The average outcome is not enough. Decision-makers must understand the full range of possible outcomes, especially the downside. Sixth, adaptive management requires pre-committed decision triggers. If we wait until a problem becomes obvious before deciding how to respond, organizational pressure may prevent action. Seventh, decision quality is not the same as outcome quality. A good decision can produce a bad outcome because of uncertainty. And a bad decision can occasionally produce a good outcome because of luck. Therefore, organizations should evaluate the quality of the decision process, not simply the final result. These 7 principles form the heart of the book. They also lead to a broader conclusion. The future of oil and gas will undoubtedly bring better sensors, better simulations, better artificial intelligence, better digital twins, and more powerful computing. But none of these technologies changes the fundamental nature of the subsurface. The reservoir remains partially hidden. The geological model remains an interpretation. The forecast remains probabilistic. And uncertainty remains unavoidable. So the competitive advantage will not necessarily belong to the company with the most sophisticated technology. It will belong to the organization that can learn faster, challenge assumptions earlier, integrate disciplines more effectively, recognize uncertainty honestly, and adapt before uncertainty destroys value. That is the real meaning of subsurface decision intelligence. It is not about predicting the underground perfectly. It is about making decisions that remain rational even when our prediction is wrong. Because in the end, the greatest challenge in subsurface engineering is not building a perfect model. It is making the best possible decision with an imperfect understanding of reality. And that is the central message of deciding the underground. Better models matter. Better data.